All right, let's continue on through Chapter 3. Section 3.3 is a measure of relative standing and box plots. Let's get into it. Some key concepts from Chapter 3.3. This section introduces measures of relative standing, where relative standing are numbers showing the location of data values relative to the other data values within the same data set. Related to relative standing, we'll cover the z-score and how to calculate that. That's the most important concept in this section. Though also importantly, we'll go through percentiles and quartiles, and from there, we'll be able to create a box plot. Now, before we move on to the rest of Chapter 3.3, recall from previously in the chapter, we know that certain percentages always fall at 1, 2, or greater than 2 standard deviations from the mean. Right, recall this is Chebyshev's theorem, where, for example, at least 3/4 or 75% of all values lie within 2 standard deviations of the mean when k is equal to 2, and when k is equal to 3, at least 89% or 8/9 of all values lie within 3 standard deviations of the mean. Now, these are sort of spread out, right? We have 75% and 89%. What if we want to calculate percentages in between these values where k wouldn't be a whole number? What would we do? Well, the most convenient way to do this is by constructing a table of values and shift our data so we can look up percentages on one reference table. This is where the idea of z-scores come in, and we're going to cover that today. Now, we'll get more into this in Chapter 6, but in Chapter 6, we'll use a table constructed for a normal distribution with a mean of 0 and a standard deviation of exactly 1. Now, from this point in the semester, you may realize that a mean of 0 and a standard deviation of exactly 1 seems pretty rare. So these properties of a mean of 0 and a standard deviation of 1 are very specific properties of a distribution, and we call this a standard normal distribution. So although we might not calculate data where we have a mean and a standard deviation of these values, we can shift our data so that it does have a mean of 0 and it does have a standard deviation of 1. Now, after we shift our data and calculate a z-score, our result will tell us directly how many standard deviation values above or below the mean our data value of x lies. Where if that score is positive, then our x data value is above the mean by a certain number of standard deviations. And similarly, if that score is negative, then our x value lies a certain number of standard deviations below the mean. And we'll get into this today, and we'll see this again in Chapter 6. This shifted value I've been talking about, this is called our z-score. We can calculate a z-score for both a sample and a population. So for a sample, this is the equation. So our z-score is equal to x minus x bar divided by lowercase s. Where for a population, we calculate the z-score as x minus mu all over lowercase sigma. Now, hopefully at this point, these all look familiar. So on your own, I want you to recall what each of these symbols means, okay? Okay, so now more on z-scores. A z-score could also be called a standard score or a standardized value. It's the number of standard deviations that a given value x is above or below the mean of the set of data. And from the last slide, we know the z-score can be calculated for both a sample and a population. It's always good to talk about how we round off these values. So for z-scores, we can go up to 2 decimal places. So for example, 2.31, we have 2 digits past the decimal place. And we'll practice this so this becomes more clear to you, hopefully. Let's go through some important properties of z-scores. Number 1, a z-score is the number of standard deviations that a value x is below or above its mean. That's where, for example, we have a data set of 10. Then each one of those pieces of data in the whole data set is considered x. X describes generally each data point in a data set. So if we have a data set, we calculate the mean. We can choose any of those 10 values in our data set and find out how many standard deviations above or below that value x is in relation to the mean of that data set. Number 2, z-scores are expressed as numbers with no units of measurement, okay? That was unlike our standard deviations and our variances. Here, z-scores have no units. Number 3, a data value is significantly low if the z-score is less than or equal to -2. Or the value is significantly high if its z-score is greater than or equal to +2. And we'll do an example of this where we determine the significance. Number 4, if an individual data value is less than the mean, its corresponding z-score is a negative number. Okay, so this is saying that we can have negative z-scores, right? So a negative z-score would indicate that that individual data value x is less than its mean. Let's talk through an example now. So we're going to compare a baby's weight and adult body temperature. Now for an example of determining z-scores and interpreting z-scores, let's ask, which of the following two data values is more extreme relative to the data set from which it came? Okay, so these are the sorts of questions we ask when we want to determine a z-score. The first data value is 4,000 grams is the weight of a newborn baby. This is among 400 weights, where the sample mean of those 400 data points is x bar is equal to 3,152.0 grams. And the sample standard deviation is already calculated here. It's lowercase s is equal to 693.4 grams. One thing I want to point out is both the mean and the standard deviation have units included. We're going to compare this to a 99-degree Fahrenheit temperature of an adult was measured among 106 adults, where the sample mean was measured at x bar is equal to 98.20 degrees Fahrenheit, where the sample standard deviation, or lowercase s, was calculated to be 0.62 degrees Fahrenheit. Now again, our question is, which of the following two data values comparing 4,000 grams and 99 degrees Fahrenheit, which of those is more extreme relative to the data set from which it came? So when we see a question like this, we're going to calculate the z-score in order to answer this question. Here are two data sets again. In order to standardize each data point, we're going to convert each to a z-score. This is how we do it. We call that to calculate a z-score for a sample. We have x minus x bar all over lowercase s, which is the sample standard deviation. Here, when we plug in our values, x is our data value that we're interested in, so 4,000 grams. X bar is the calculated mean of the sample, so that's 3,152.0 grams. We divide that by the standard deviation, which in this case is 693.4 grams. Therefore, for this data point, we get a z-score of 1.22. Now let's do the same for 99 degrees Fahrenheit. Plugging in our data value, our x bar, and our standard deviation, we get a z-score for this data point of 1.29. Let's now compare these z-scores and interpret what it means. So for 4,000 grams, we calculated a z-score of 1.22. That means that this weight of 4,000 grams is 1.22 standard deviations above the mean. Similarly, for 99 degrees Fahrenheit, we calculated a z-score of 1.29. That means that 99 degrees Fahrenheit is exactly 1.29 standard deviations above the mean. And these are both respective to the data sets they came from. Now from this, because the body temperature is farther above the mean from the sample of data it came from, it is the more extreme value, right? So 1.29 is greater than 1.22. Therefore, we can say that a 99-degree Fahrenheit body temperature is slightly more extreme than a birth weight of 4,000 grams. We say slightly here because 1.29 isn't drastically greater than 1.22. Okay, so here we calculated a z-score for sample data, and then we were able to interpret those z-scores. Okay, now I mentioned significance already, but here's how to visualize it. So significant values are those with z-scores that are less than or equal to -2.00, so that's on this side of this figure. Also, if z-scores are greater than or equal to +2.00, these are also significant, where on this side, these are significantly low values, and over here, these are significantly high values. I also told you we'd do an example, so here we go. So the lowest platelet count in a data set is 75. Platelet counts are measured in 1,000 cells per microliter of blood, typically. So now we ask, is that value significantly low? Here we can assume that the platelet counts have a mean of X bar is equal to 239.4 and a standard deviation of lowercase s is equal to 64.2. Recall that both X bar and standard deviation do include units, where the units are measured in 1,000 cells per microliter. So we didn't write that out here, but this is the unit that we would include. So now how do we answer this question? Is this platelet count of 75 significantly low? Let's find out. So what's the first thing we need to do? Is to convert 75 into a z-score. Let's do that. So again, this is the same formula because we're dealing with a sample and not a whole population. So z-score is equal to the data point minus the mean for that data set divided by the standard deviation for that data set. Here we're interested in the data value of 75. The mean is 239.4 and the standard deviation is 64.2. Here we calculate a z-score of negative 2.56. So a couple interesting things here. We have a negative value and this value is less than or equal to negative 2.00. So what can we conclude? So a platelet count of 75 converts to this z-score. Now, this z-score is less than negative 2.00. That's our cutoff for saying if a number is significantly low. So here, yes, this platelet count of 75 is considered significantly low. And here's the medical name for low platelet count in case you may be interested in going to medical school or going into being a physician's assistant. It's thrombocytopenia. That's not something you need to recall for our statistics class, but there it is. The next part of this section is talking about percentiles and quartiles. We're going to talk about percentiles first. Percentiles are defined as measures of location. They're denoted by a capital P with a subscript, where that subscript denotes the percentile. So this would be the first percentile, this example, second percentile, this number, 99th percentile. Okay, so we do capital P and then a subscript to denote the percentile. Now, if we have percentiles, this divides a set of data into 100 groups, right? 100 percentiles, with about 1% of the values falling into each of those groups or into each of those percentiles. Let's talk about how we'd find the percentile of a data value. So this is the process of finding the percentile that corresponds to a particular data value X. And remember, each individual data value is denoted by X. So this is given by the following, and we round to the nearest whole number after calculating this percentile. So here's the equation. The percentile of some value X is equal to the number of values less than that data point of X divided by the total number of data values multiplied by 100 to get this value into a percent. We'll do an example of this. So here's these Verizon cell phone data speeds in megabits per second that we've seen a few times. One thing you'll notice is this data is already sorted in ascending order. So it goes from 0.8 to 1.4, where this is the minimum data value, all the way to 77.8, where this is the maximum data value. Here we're asked to find the percentile for the data speed of 11.8 megabits per second. Now here's 11.8 megabits per second within our data table. So let's determine the percentile. Let's calculate that. So from our data table, we identify 11.8 being here. Now recall from the equation for percentile, we need to determine the number of data points less than that value of interest and the total number of data points. So here if we count, then we have 20 data speeds that are less than 11.8. Remember, we're interested in 11.8 specifically here for this example. We can also determine the number of total data points. So here we have 1, 2, 3, 4, 5 rows multiplied by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. So 5 times 10, we have 50 data points total. Now going back to the equation really quickly, we calculate the percentile of our value X by taking the number of values less than X divided by the total number of data values multiplied by 100. So let's put in our numbers here for this example. So for the percentile value of 11.8, we have 20 data values that are less than that data value of 11.8, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2. We have 20 data values less than 11.8. Now we divide 20, so the number of data points less than 11.8, divided by 50, the total number of data points here in this data set. Then we multiply it by 100 to get 40%. So this means that 11.8 is in our 40th percentile. Now again, here a data speed of 11.8 megabits per second, that indicates it's in the 40th percentile based on what we just calculated. This can be interpreted loosely also as a data speed of 11.8 megabits per second separates the lowest 40% of data values from the highest 60% of data values. So in other words, the lower number of percentile, that indicates that the value is on the lower end of those data values. And the higher percentiles mean that the scores, the data values are higher. The way to denote this with symbols is we have our capital P subscript 40. That means we have our 40th percentile, where we just calculated that 11.8 is the number in the 40th percentile. Now in your student outline, there's another example to try. Let me know with any of these problems in your student outline if you want to check any of your answers. Now, some notation to go through, and I think it's easier once we actually implement that notation and we calculate it, but it's important to recognize the following. N is the total number of data values in the data set. We've seen that before, where lowercase n reflects a sample and uppercase n reflects the population. Next, a new one here. So lowercase k indicates the percentile being used. So for instance, the 25th percentile, this can also be denoted as lowercase k is equal to 25. Next, another new one here. So uppercase L is the locator that gives the position of a value. Now, for example, if we have that whole data table of data speeds and L is equal to 12, that means that we're talking about the data value that's in the 12th position. It's the 12th value in that sorted list. Right, so we could count data point number 1, 2, 3, 4, 5, where data point number 1 was our lowest value in the data set, and data point number 5 was that 5th data point in the data set. So this capital L just means the location of the data point. And we'll practice doing calculations with all this notation. Combining these two now, what we've talked about, so the percentile, where percentile is capital P. Here, if we have capital P, lowercase k, we've covered this one now. So this means we're looking at the kth percentile. In other words, we saw this already, right? Capital P subscript 25 means this is the 25th percentile. Okay, and so try not to let the notation be too confusing. Let's practice using it. These are directions here for converting a percentile into a data value, and we're gonna go through these steps. Okay, and as we go through the steps, I'm going to talk you through the flowchart. Let's just dive into it. So here's an example. We're going to convert a percentile to a data value. This question says, refer to the sorted data speeds below, find the 40th percentile. And remember, this is denoted by capital P and then subscript 40 to indicate the 40th percentile. Now in that flowchart, we start, and then the next step is to sort the data, which means arrange the data in order of lowest to highest. So this is already done for us. We have 0.8 up to 77.8. That's the very first step in doing this, converting a percentile to a data value. And I want to mention, we took 11.8 and we figured out what percentile this is in. This is going the other way. So we're given a percentile and we need to figure out what data value that refers to. Another important step here to do that's not indicated explicitly in the flowchart is to total the number of data values. Here we already figured out that with 5 rows and 10 columns, we have 50 data points total. We're going to need that value later. Next in the flowchart, we're going to compute this. And remember our notation we just went over, where L is the locator, K is the percentile in question, and N is the number of data values in the data set. So let's practice using this notation. So in solving these problems, we need to figure out L, because then once we know where the data point is located, then we can identify the data point. Now to figure out our other variables here, K is 40, right? So K is the percentile in question. And here we're asked to find the data point that is the 40th percentile. So here k is equal to 40. The other variable here is the number of data values, right? I told you we'd use that, so we have 50 data values total. Now, plugging in these variables, we have capital L, the locator, is equal to k over 100 times n, where k is the percentile in question, so we plug in 40. We divide this by 100, that's part of the equation, and multiply it by n, the number of data values, where the number of data values is 50 in our case. Then here we know L, the locator, is equal to 20. Now another part of the flow chart that we should talk about. So since L is 20, that's a whole number. Now this doesn't mean that number 20 is our sample number that's in the 40th percentile. This means that the locator is number 20. So let's continue on with the flow chart. So L is the locator. We calculated capital L to be 20. 20 is a whole number. So now in that flow chart, very importantly, we need to refer to this part now. So when L comes out to a whole number, we need to take that number value where we take the 20th value in the sorted data set. But very importantly, we need to take the 20th value, the Lth value, and the next value in the sorted set of data. This is very important. So we don't just take data point number 20, we take data point number 20, and in this case, data point number 21. And we actually find the mean of data point number 20 and data point number 21. So we take data point number 20, add it to data point number 21, and divide that sum by 2. So in other words, based on our example here, we see that the value of the 40th percentile is midway between the 20th value and the next value, where that next value in our case is the 21st value. Now let's look at this table again. So if we count these data values, this is data point number 20, this is data point number 21, so we're getting closer here. So because 11.6 is data point number 20, 11.8 is data point number 21, we need to take the mean of those two values, where the mean is 11.7. Okay, so I've typed this out, what I just told you. So what we can ultimately conclude is that the 40th percentile, what we were asked for in the beginning, the 40th percentile for this data set is equal to 11.7 megabits per second. Now, if you're wondering why I included the unit here, we do include the unit for p-values, for percentiles. We don't include the unit for z-scores, right? Okay, now I mentioned we're going to go through percentiles and quartiles. Quartiles are very similar to percentiles, but quartiles, they're also a measure of location, but they're denoted as Q1, Q2, and Q3, not as P1, P2, P3, P4 through P99, right, as we did for percentiles. So for quartiles, again, we use Q1, Q2, and Q3, and we divide the set of data into 4 groups by doing so, with about 25% of the values in each group. Now, again, we just talked about percentiles, and I spoke on this, but recall for percentiles, these are denoted as P1, P2 through P99, which we divide the set of data into 100 groups total, rather than just 4, with about 1% of the values in each group. Where for quartiles, about 25% of the values are in each group. Okay, let's talk a little bit more about quartiles, and we'll do an example. So Q1 is the first quartile. This is the same as thinking about the 25th percentile. In other words, it separates the bottom 25% of the sorted values from the top 75% of the sorted values. Next is Q2. This is the second quartile. This is the same as thinking about P50 or the 50th percentile. It's also the same as the median. If you recall what the median is, it's the value that appears directly in the middle of a data set. The second quartile separates the bottom 50% of the sorted values from the top 50% of the sorted values. Now it's important that I keep saying sorted values because first you have to list them from lowest to highest. Otherwise you can't do these calculations in the same way. Okay, so you have to list your data values first in ascending order. The third quartile, or Q3, this is the same as thinking about P75 or the 75th percentile. It separates the bottom 75% of the sorted values from the top 25%. Now, another way to visualize this, let's say we have our bottom 25% of our data points, 25 to 50, 50 to 75, and the top 75 to 100 data values in our data set. And this isn't saying anything about importance necessarily, it's just the numbers that are on the lower end in our data set and numbers that are on the higher end and ones that are in the middle. Where using our quartile notation, Q1 would be the value here, or P25, Q2 would be the value here, or P50, the 50th percentile, and Q3 here, or P75, the 75th percentile. And we will definitely do examples of all this. One word of caution here, occasionally if you're computing quartiles using a calculator or a graphing calculator or Excel or a different statistical programming method, you can get slight variations in your quartile numbers. This is also true for percentiles, it's just something to be aware of. Now, using what we just learned, so quartiles and percentiles, we also first need to define a few different terms. The first is this interquartile range. This is also abbreviated as IQR, so interquartile range. We find the IQR by taking the value of Q3 minus the value of Q1. The next term here is the semi-interquartile range. We calculate this by taking Q3 minus Q1, which is the IQR, the interquartile range, and we divide that by 2. The next term is the mid-quartile range. This is Q3 plus Q1 divided by 2. The fourth important point here is this 10 to 90 percentile range. This is somewhat more self-explanatory based on the name. We take the percentile value that's the 90th percentile, we subtract it from the value that's the 10th percentile. Okay, so 10 to 90 percentile range. Now, we could calculate a variety of numbers now, right, based on a data set, different percentile values, different quartile values. One thing that's kind of nice is that we have this 5-number summary, and sometimes we're asked just to calculate the 5-number summary for a set of data, rather than all these other data points. Now, the numbers that are in this 5-number summary include the minimum value, the first quartile or Q1 value, the second quartile or Q2 value, remember this is the same as the median, the third quartile or Q3, and lastly, the maximum value in that data set. Let's do this example of finding a 5-number summary for this same set of data we've been working with. Now recall in that 5-number summary, we're looking for the minimum and the maximum data value. So here, because this data is sorted, which you should do before analyzing the sorted data, so we can see pretty easily that the minimum data value in this sorted list is 0.8. Also, we can see that the maximum data value in this sorted list is 77.8. Now, we also need to practice calculating quartiles now. So let's do this. Q1 is also required as part of the 5-number summary. So when we're calculating Q1, it's our first quartile. Remember, this is the same as thinking about this being the 25th percentile, or P25, where the first quartile separates the bottom 25% of the sorted values from the top 75%. Now, we've done this before, right? We use this equation. Now let's figure out what numbers we would plug in here. Remembering that Q1, the first quartile, that's the very same thing as thinking about calculating the 25th percentile, and we've done this before. So taking this equation, the 25th percentile, that means that K here is going to be 25, N, the number of data values, that's going to be 50. We can calculate L, and then we can figure out what data value is the first quartile, or Q1. So let's try this. So we're going to take 25 divided by 100, that's in the equation, multiply it by 50, we get 12.5. Now, what do we do if this isn't a whole number? We looked previously at an example where this was a whole number. So go back a few slides if you need to remember that, where if you went back a few slides, we would go this direction on the flowchart when it is a whole number. Now let's talk about this part of the flowchart when L is not a whole number. So to account for this, we change L by rounding it up to the next larger whole number. Okay, the key point here is we take L, we round it up, okay? Okay, so now back to this slide. When L is equal to 12.5, what do we do with it? We round it up to the next whole number. Now in this case, when we round up 12.5, we get 13. So now we know the locator number is 13. So what do we do from there? We count out. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So our locator number of 13 tells us to go to data point 7.9. So from this calculation and from this information, we can say that the value of the first quartile, or Q1, which is the same as the 25th percentile, or P25, that value is 7.9 megabits per second. Okay, so far we have the minimum data value, the maximum data value, and now we just calculated Q1. Let's do this for the remaining numbers in our 5-number summary. So next we need to calculate Q2, or the second quartile. We can think of this as the same thing as being the 50th percentile. Now we're going to use that same equation again, where our percentile is 50, and we still have 50 data points in our data set. So to calculate our locator number L, we take 50 now for our percentile of K, still divide it by 100, multiply it still by the total number of data points of 50, and we get 25. Now, importantly, 25 is a whole number. So what do we do with whole numbers based on that flow chart? Well, we take the 25th value and also the 26th value. So now if we were to count this, we would find that 13.7 is the 25th data value in the data set. Now also 14.1 then is the 26th data value. So in order to find Q2, we need to take 13.7, add it to 14.1, divide the sum by 2. That means that we just calculated Q2 being 13.9 megabits per second. Now this is a good refresher. Remember, for calculating the median, we had a way to do this based on an odd number of data points and an even number of data points. If you need a refresher on that, I recommend going back and looking at the slides on calculating the median. Now we just have one more of our 5 numbers to calculate. Doing the same thing we did for Q1 and Q2, we can do this for Q3. Now I've written this out, so we take the locators equal to 75 because we're working in the 75th percentile, because we can think of Q3 as being equivalent to P75, or the 75th percentile. So that's one other really important thing here, is to know the equivalencies between the quartiles and the percentiles. So we take 75 divided by 100, we're still multiplying it by 50, the total number of data points. Here we get 37.5. What do we do when it's not a whole number? We round that up to the nearest whole number, so that's 38. Okay, so the key here, we round it up, right, if it's not a whole number. So if we were to count this out, we'd find that the 38th data value here is 21.5 megabits per second. That means that Q3 is 21.5 megabits per second. There are 2 additional examples for you to try in your student outline. Again, let me know if you want to check any of your answers. Now, our 5-number summary for this data set is therefore 0.8, 7.9, 13.9, 21.5, and 77.8. Note how we listed these in order of ascending order, where we started with the minimum value, then Q1, Q2, Q3, then our maximum value, and still importantly, these are all in units of megabits per second. Now, similarly, we're going to take our values that we learned how to calculate for quartiles and percentiles and apply them to a box plot. You may also hear them called as a box and whisker diagram, but I'll probably just call them box plots. That's what I'm used to. Where a box plot is a graph of a data set that consists of a line extending from the minimum value to the maximum value. And there's a box with lines drawn at the first quartile, Q1, the median, or Q2, and then the third quartile, or Q3. Now let's go through the procedure for constructing a box plot. Number 1, we're going to find that 5-number summary that we just did. The minimum value, Q1, Q2, Q3, and the maximum value. You have to do that before you can construct a box plot. Then we construct a line segment extending from the minimum data value to the maximum data value. Then we add a box or a rectangle extending from Q1 to Q3, and we draw a line at Q2, which is the median. And because we would have already calculated our 5-number summary, this should be relatively straightforward. Now let's go back to this data set and construct a box plot for it. Number 1 was to find our 5-number summary. We have already done this. Right, so our minimum value, Q1, Q2, Q3, and our maximum value, we already calculated. The second step here is to construct a line segment extending from the minimum data value to the maximum data value. So here we have 0.8 to 77.8. So here, for example, our first data point here would be our minimum value of 0.8 and our maximum value of 77.8. You can add these lines here if you want. The third step is to construct a box or a rectangle extending from Q1 to Q3, and we draw a line to represent Q2 or the median. Now, since we've already calculated the 5-number summary, 7.9 is Q1, Q2 is 13.9, Q3 is 21.5. So we draw a box from Q1 to Q3, and then that line here occurs at Q2. So here's our final answer for a box plot that represents this data set. Now, we talked about skewedness looking at histograms. We can also look at how data sets are skewed looking at these box plots. Now recall that to identify skewedness, it's a distribution of data that's not symmetric. So in other words, it extends more to one side or the other. So we could visualize that pretty easily with histograms. Now with box plots, we think the same way for skewedness. So recall from our histogram section, data skewed to the right was positively skewed. That means there was actually a longer tail to the right and the data was sort of focused on the left. Okay, so it's important not to get these directions of skewedness mixed up. Okay, so we also have skewed to the left or negatively skewed. That means that we have a longer tail of data on the left and our data is sort of focused on the right now. Okay, so these labels may or may not be intuitive to you, but definitely keep them clear either way. Now, for example, we just made this box plot for our data. Can we identify any skewedness here? So yes, we can, right? The data is focused on the left side, so we could imagine there being sort of a tail here towards the right. Now, because this tail would be sort of to the right, then this is an example of a positively skewed set of data. It's skewed to the right, where we have a longer right tail and relatively few values are high data values, and most data values are here to the left. Now, one other really important property of box plots is they can be used to identify outliers. Now, we've talked about these a lot before, so let's work on an example with them. And when we're using box plots to identify outliers, we can make more of a modified box plot, and I'll show you what that looks like. We'll do an example. Now, the steps for identifying outliers. We have first to find the quartiles Q1, Q2, and Q3. You have to do that first before we can identify outliers. And ideally, you've already done this because you have the 5-number summary for a set of data, so then you already have Q1, Q2, and Q3. Next, we need to find the inner quartile range, which we spoke about before. This is the IQR. We take the data value for Q3 and we subtract the data value for Q1. The third step here, we evaluate 1.5 times the IQR value. Then we can make a modified box plot from here. So in this modified box plot, a data value is an outlier if it's above Q3 by any amount greater than 1.5 times the IQR. It's also an outlier if it's below Q1 by any amount greater than 1.5 times IQR. And we will do an example of this. First, let me clearly define a modified box plot. So this is a regular box plot, but it's constructed with these modifications. One is that we have a special symbol. It's an asterisk, a star. These are used to identify the outliers. And we'll go through an example of how we identify outliers, but it was defined how we do that on the previous slide. Also in a modified box plot, now the solid horizontal line only extends as far as the minimum value that is not an outlier and the maximum data value that is not an outlier. And I will show you an example of this on the next slide. Now with the data set we've been working with, the first step here was to find Q1, Q2, and Q3 for identifying outliers. Next, we calculate the IQR, so we take Q3 minus Q1. In this case, our value for Q3 is 21.5. And in this case, also our value for Q1 is 7.9. So 21.5 minus 7.9, our IQR here is 13.6. Next, we take our inner quartile range, or IQR, we multiply that by 1.5. So 1.5 multiplied by 13.6, we get 20.4. Now to better set us up for identifying the outliers, we can calculate these two values, and we should calculate these two. So recall that a data value is an outlier if it's above Q3 by any amount greater than 1.5 times IQR. So in this case, Q3 was 21.5. Our value for 1.5 times the IQR is 20.4. So when we add those two together, we get 21.5 plus 20.4 is equal to 41.9. That means that any value greater than 41.9 would be considered an outlier. Now on the other end of the data, a data value is an outlier if it's below Q1 by any amount greater than, again, 1.5 times the IQR. Now to calculate that numerically, we take Q1, we subtract 1.5 times the IQR. So for here, we have 7.9 minus 20.4 is equal to negative 12.5. Now I think it's important to calculate these first. And now let me show you what this looks like on a modified box plot. Here's our set of data again. We're always going to draw something like this for a modified box plot and for a regular box plot. But here on the left-hand side, we go to the lowest value that's not an outlier. Here, 0.8 is certainly still greater than negative 12.5. So in this case, the lower value for our modified box plot is the same as it would be for our regular box plot. Now let's see the other end. So here for a modified box plot, the end here needs to represent the highest data value that's not an outlier. Now from here, step 4, we determine that any value greater than 41.9 is an outlier. So let's go to our data set, 41.9. That looks like it would separate right here. So any data value greater than 41.9 is an outlier, and any data value less than 41.9 would not be an outlier. So that means that this end of our modified box plot is 38.5. One more very important step left is to actually identify the outliers. Again, there are no outliers on this lower end of the data set, but here we're separating the line here where 43.0 is greater than 41.9. So that value is an outlier. Similarly, so would 55.6, 71.3, and 77.8. These are all outliers because they're greater than Q3 by an amount greater than 1.5 times the IQR. Now to indicate this on a modified box plot, we add in our asterisks and then we have each data point labeled. Ideally also we have each data point somewhat separated in a way that scales. So here 71.3 and 77.8 would be closer together ideally than 71.3 and 55.6. The important part here is that we represent all the outliers and we do so with an asterisk. Okay, that is officially the end of chapter 3. Recall that exam 1 covers chapter 1 through chapter 3. I do want to put another reminder in here about the importance of doing these practice exams and doing them before the exam. So the practice exams are due midnight before the day of your exam, and absolutely no late work can be accepted for these extra credit assignments. I also want to point out that if you're doing sample practice problems, some of the answers are in the back of your textbook. Okay, so I hope you've been keeping up with the material. I hope you've been keeping up with your MyStatLab homework, and I hope you're feeling in a pretty good place to be ready for exam 1. Let me know if I can help with anything at all. I hope you have a great day, a great evening, a great morning whenever you're watching this, and I'll hopefully see you all soon.